It's just great to see so many companies focused on this really critical. Oh, I think I need the slide clicker. Here? All right. So many companies focused on such an important category of disease, which is neurological diseases. So I'm going to introduce Bloom Science very briefly. We're a San Diego-based biotech platform company focused on the gut-brain axis. And really, this takes a platform that was developed by Elaine Shao at UCLA that combines this kind of deep multi-omic data analytics approach with very traditional phenotypic screening to uncover novel therapeutic opportunities and target discovery. Before I get into that, though, let's take a step back. We talk about the gut-brain axis. You know, we've known about the gut-brain axis and the relationship for thousands of years. The ancient Greek, the ancient Chinese, in fact, even the ancient Incans actually detailed the important role in human health. And of course, the focus recently has really been on our friendly neighborhood microbes that exist in our gut microbiome. One of the fundamental things that we forget about is the input into the system, and that's our diet. Now, over the last 6-7 decades in the Western world, and over the last 2 to 3 decades in Asia, we've seen this incredible increase in neurological conditions: Alzheimer's, epilepsy, autism. At the same time, we've seen a massive disruption in the input, right? Industrialized agriculture, exposure to agrochemicals, and even fundamental things like how we feed our babies. So we see this massive disruption in our gut and in our brain function. And that's really where we want to focus on. So on the far left here, we really understand at a much more detailed level than the ancient Greek, that role and that relationship between the gut microbiota and the brain. So the microbiota in the gut play a role in neurotransmitter biosynthesis and regulation. They play a role in immunology. They play a direct role in communication through the vagus nerve from the gut to the brain, as well as deliver a number of metabolites that have an effect on metabolism. So what's emerged as a model is this model of dysbiosis, right? Healthy brain, healthy gut, abnormal brain function, abnormal gut. And we see this with Parkinson's. In Parkinson's patients, they have a disrupted gut. Now, as a therapeutic discovery point, this is very challenging. It's important, but it's challenging because there's 2 fundamental questions that we don't know. Is this a chicken or the egg? Are we having disrupted gut function because of the disease, or is the disease a manifestation because of disrupted gut? We don't know. The other thing is, if we look at a 2-state problem, those 2 states, if we're comparing them, need to be well defined. And we know that there's no such thing as a healthy microbiome. There's multiple healthy microbiomes. It's a range. So we think this is challenging in an already challenging space. So we take a very different approach. We look at dietary interventions that are already associated with positive clinical outcomes. So very specifically, ketogenic diet and intermittent fasting. And for those who aren't familiar, the ketogenic diet and intermittent fasting are therapeutic diets. They've been around for over 100 years. They're clinically validated. And we know quite a lot about these diets in terms of mechanism. So if we can actually pull out a little, oops, sorry. So we know that these affect all these very important pathways: mTOR, PPAR, HTAC. They have an impact on synaptic plasticity, on ROS. So we understand the underlying mechanisms involved in this diet. Bloom Science's goal is to reverse translate these into basic principles and look at that therapeutic opportunity. How do we do this? So we start with clinical trials with patients on these therapeutic diets in a variety of different indications, from epilepsy, Alzheimer's, glioblastoma, and we put them through our very deep multi-omics platform. But we not only collect the whole genome sequencing and the metabolomics from these samples, we also look at patient outcomes. We look at patient history. We look at genotyping of these patients, so we begin to extract insight. Now, as we cluster these different signatures, we want to actually test those in these animal models that are relevant to our interests. And this is really critical as well, because again, we need to functionally annotate the changes that we observe from these patient samples. Yes, we'll have outcome data, but oftentimes outcome data is complex because a lot of it, particularly in this space, relies on self-reporting. So from this platform, we see 4 very primary opportunities. And that's in novel therapeutic development, identification of microbiota-based molecules or metabolites, a novel target discovery, and diagnostics. So this is what makes Bloom Science unique. It's really this focus on the gut-brain axis, but really starting not necessarily in the space of dysbiosis, but in the space of positive clinical outcomes, putting it through this platform with validated samples. And I think what also makes this quite unique is that we have a lead program that we believe is poised for an IND that's come out of this research. And it's actually the combination of 2 commensal gut bacteria that reduce seizures in 2 separate preclinical seizure models. We can demonstrate changes in regulation of key brain neurotransmitters, and we have this predictive metabolite signature that we've developed that we think is a great basis for biomarker development. And so Bloom Science at a glance, again, I can't go through every program, but really building out this platform, we actually not only collaborate with clinicians, but we have our own in-house clinical sample collection study, which we call Poo for Science and Poo for Epilepsy. And we're working with patient advocacy groups to directly reach out to these patients, collect their samples, as lots of companies have done. But our goal is not only to get that data sample, but to be able to have the fecal samples to put back into the mice. Okay, and then any platform's value really comes to what you can extract out of it in terms of therapeutic programs. So I've detailed our lead program is actually in epilepsy, refractory epilepsy. Epilepsy is quite prevalent in the world, but there's really 2 pain points. The first is 50% of patients that do respond to anti-seizure drugs have significant side effects. Second part is 1/3 of all epilepsy patients don't respond to anti-seizure drugs. Of those patients, that population, there's really only 3 solutions. Continue to screen through these anti-epileptic drugs, which there's a less than 5% chance they'll respond. If they might be eligible for surgery, they'll undergo surgery, or the ketogenic diet. And as I mentioned, the ketogenic diet's been around for 100 years to treat seizures. It's as efficacious as anti-seizure drugs. So if we try to reverse translate that, what do we get? Again, this is condensing a huge amount of work, but really to highlight, again, we have reduction of seizures in 2 different preclinical models by administering these 2 commensal bacteria. We can see changes in GABA and acetylcholine in the hippocampus when we do hippocampal metabolomics. So not only are we looking at the phenotypic output, but we're understanding the underlying mechanism that we can also extend to other indications. I'm going to skip this for time. What's also interesting, again, is not only at looking at bacteria as bugs as drugs, but how do we develop this insight around novel target discovery as well as novel bacterial metabolites? And here, looking at one of the targets that we've identified and trying to understand what these bacteria are doing, we can target this enzyme. It's never been shown to have a role in epilepsy or in seizures, but we can target and get some significant seizure protectiveness. What's also quite interesting is we know that one of these bacteria has this enzymatic activity, but when we co-culture it with the other bacteria, we eliminate that activity. So this is suggestive that there are some novel bacterial metabolites driving this behavior. Finally, and I'll get to, I think I have just my second to last slide, is how do we expand this platform outside of epilepsy? So intermittent fasting is also a therapeutic treatment for multiple sclerosis. And there's been quite a number of studies. This is where we've taken, this is where one of our collaborators has looked at intermittent fasting and reimplanting the fecal samples from the mice that are treated with that back into naive mice and looking at the reduction of the pathology within this model. Just this intermittent fasting drives Treg upregulation of Tregs and a decrease in inflammatory T cells. What's really interesting is that we see similar changes in the microbiota between the human sample patients as well as the mice. So a way for us to dive in to this biology as well. I'll finish with our team. You know, this is a rapidly evolving space. Epilepsy itself is very complex. So we really try to tap into some experts in the field to be able to really drive value out of this platform. So I thank you for your time.